Hello and welcome back. My name is Dr. Mark Taylor. This is the Delaware Tech Physics 111, Lesson 11B, Part 3. Lesson 11B is the first lesson of Unit 4 on electricity and circuits. And in this video, we will continue with methods of charging and Coulomb's law. Okay, what do we mean by methods of charging? Methods of charging refers to taking an object that is neutral in charge, in other words, no net charge. It can have lots of positives and lots of negatives, but they balance each other out and there's no total charge. There's no net charge on the object. And methods of charging refers to taking that object and putting a net positive or negative charge on it. And we have three basic ways of doing this: charging by friction, charging by conduction, charging by induction. And charging by friction is probably the easiest one to understand. This is literally just taking two different objects made of two different materials, rubbing them together, and one of them steals electrons from the other. So one becomes negatively charged and one becomes positively charged. And we'll go over each of these. The second one, charging by conduction, we've actually already talked about this when we talked about the conducting balls touching each other. But if you imagine you have a situation where one object, one conducting ball, has a charge and the other has no net charge on it, when they contact each other, charges will flow between these two objects and the formerly uncharged object will become charged, as long as the two objects are made of conducting materials like metal. And the third method is the hardest one to explain, and when we get to the diagrams, it should be a lot easier. But a charged object is brought close to an uncharged object without touching. In other words, you have this object that has a positive or negative charge, and you bring it near the second neutral object, but you don't touch it. What will happen is the positive and negative charges on the second object, keeping in mind the second object is neutral, but it has lots of positive and negative charges that balance each other. Well, these charges on the neutral object will separate. They'll polarize, and you'll have the positive charges on one side of the object and the negative charges on the other side of the object. And then we have very simple ways to get rid of half of those charges, leaving that originally neutral object now with one of those two charges. So let's talk about these in a little more detail. So charging by friction, as the name suggests, you literally are rubbing two objects together. And the objects could be a comb running through your hair. It could be a piece of wool cloth rubbing on a glass rod. It could be a piece of silk cloth rubbing on a chunk of amber. Amber is just fossilized tree sap, tree resin. And when that happens, one of those two materials prefers to have the electrons more than the other, so the electrons will literally jump from one object to the other. The object that gains electrons will become negatively charged. The object that loses the electrons will become positively charged. And shown in this picture is a little girl here. She's had her hair rubbed with a comb, and the comb becomes negatively charged because the comb literally steals electrons from her hair. Now you'll notice the hair is sticking up, and we've all had this happen. At least I did when I still had hair. And when you comb your hair, especially in the dry winter air, your hair will tend to stand up. Well, that's because your hair is now positively charged. Each hair has a little bit of positive charge on it, and positive charges do not like being near other positive charges, just like negative charges don't like being near a lot of other negative charges. So they repel each other, and this is why your hair stands up. It's not because the hair is trying to stand up, it's because the hair is trying to get away from every other piece of hair with a positive charge on it. Now, I mentioned two other materials that could be rubbed together, amber and silk. And the reason why I mention this is if you grew up in the United States and you were asked who discovered electricity, Most of us would say Benjamin Franklin. But the fact is, Benjamin Franklin, who did his work in the late 1700s, worked with electricity, but he did not discover electricity. Electricity, or at least the effects of electricity, were discovered much, much earlier by a man named Thales of Miletus. Miletus was a Greek town in an area that's now part of the country Turkey. And Thales was a brilliant philosopher and mathematician and astronomer and engineer. And he noticed that when he took amber and rubbed it with a piece of fur, that the amber suddenly had this power to pick up small objects like little pieces of dust or pieces of straw or tiny feathers. And eventually that would go away, but he noticed when he would rub it with fur again, that power would come back. And this, in fact, was the first known discovery of some effect related to electricity. In fact, this was really a form of static electricity. But Thales of Miletus lived in the 6th century BC. So this was about 2,600 years ago that the first electrical effects were noticed. Well, why did I even tell you about this story of Thales of Miletus rubbing amber with a piece of fur? Because the ancient Greek word for amber is electron. And it is where we got the word electric and electricity, and eventually the word electron, meaning the subatomic particle that carries a negative charge and is responsible for most of our modern electricity. Now, the second method of charging we're going to talk about is charging by conduction. This is when you're touching an uncharged object with a charged one, or touching two objects together with different charges. We've already talked about situations where we have two conducting balls with different charges, and we touch them together and charges flow. And because the two conducting balls are identical in size and shape and the type of metal that they're made of, the charges that will end up on the two balls will be the exact same charge. In other words, we'll just add up the two charges, divide by 2, and that's what each ball will end up with. But since we're talking about charging by conduction, the implication here is these are situations where you're taking a ball that has no charge on it. It's a neutral ball, as shown in box A, with the right ball that has 0 coulombs of charge. The left ball has positive 12 coulombs of charge, and it could have had negative 12 coulombs of charge. Doesn't really matter as long as one ball is uncharged and one ball is charged. When the two balls contact each other, charges will flow. And eventually, because these balls are identical in size and shape and composition, we'll end up with two balls with the exact same charge on each. Now, a little side note, you'll notice because the left ball is positively charged, when these two contact one another, it's not positive charges that are moving. Remember, it's the electrons that are moving. The protons are stuck in the atoms. They don't go anywhere. It's only the electrons that are flowing. So what actually happens is in box B, when the two balls are in contact with one another, electrons from the right ball, the neutral ball, flow to the left in order to make both balls equal charge, in this case of plus 6 coulombs. And then when you separate the balls, they retain that plus 6 coulombs on each ball. And because both balls have the same sign charge, they're both positively charged, the positive charges on the left ball will repel the positive charges on the right ball, so they will stay as far apart as possible. And that's why you see the left ball's charges are on the left and the right ball's charges are on the right. Any time you have charges flowing because of contact between two conducting materials, once the two materials contact one another, electrons can freely flow from one to the other. This is charging by conduction. So the third method of charging is called charging by induction. Now, we just did charging by conduction, where conducting materials are brought in contact with one another, allowing electrons to flow through the materials from one to the other. In charging by induction, there is no contact between the charged object and the uncharged object. So a charged object is brought near, it's brought close to the uncharged object, but not touching it. And this causes the various positive and negative charges in the uncharged object to separate, what we call polarize. So typically you would do this by taking a charged rod, that's the inducing object, the object that will induce the charges on the other object to separate. It's brought near the neutral object, but they don't touch. The charged object causes the charges on the neutral object to redistribute, specifically to separate, to polarize. So let's go through this step by step. You have a diagram here with 5 panels, A through E. In panel A, initially we have a neutral object, and a neutral object doesn't mean it has no charges. It means it has an equal number of positive and negative charges. And in a macroscopic object, in other words, an object you can see, there are an enormous number of positive charges and negative charges. They happen to be equal and they cancel each other out. Now, in panel B, we bring a charged rod. And in this particular example, that charged rod happens to be negatively charged. And it's moved near the neutral object, causing the like charges, in other words, other negative charges in the neutral object, to be repelled. They're going to move as far as they can to the opposite side of the uncharged object. Uncharged object, in this case, is a conducting sphere. Meanwhile, the opposite charges, in other words, the positive charges in this case, are attracted to the negative charges in the charged rod, so they move to the near side of the neutral object. So we polarize the charges. The positive charges are on one side, the negative charges are on the other. In panel C, we do something called grounding. And if this was a lot of charges, if it was a real electrical device and we had a lot of charge on it, we would use a wire. But using this method, we don't put a lot of charge on the charging rod, and as a result, there isn't an enormous amount of charge separation on the conducting sphere, and therefore it's safe to use your hand as the ground. Otherwise, we would just use a wire. So the electrons would flow from the neutral object down your arm, through your body, and into the ground, or through a wire down into the ground. And this would leave in panel D only the opposite charges on the originally uncharged object. In this case, the positive charges are left because we used a negative charged rod. And in panel D, you'll notice the positive charges are still attracted to the negative charges in the charged rod, so they tend to be on one side. But when you remove the charged rod in the last panel, the charges on the conducting sphere, remember these are the only charges, in this case they're positive charges, and they want to get away from each other, so they will evenly distribute around the outside surface of the object. So another example of induction is actually even simpler. Now we start with a double metal sphere. So it's 2 metal spheres and they're just touching one another. So the electrons can move freely between them. They are totally neutral. They both have a lot of positive and negative charges that are exactly equal to one another. But when you bring that charged rod near it in B, and in this case, we happen to be using a positively charged rod, what happens is the negative charges are attracted to the positively charged rod, so they move to the left side of the left sphere, and the positive charges in the spheres are repelled to the right side of the right sphere. So you polarized the charges within this double sphere setup. Now, instead of dealing with grounding, you literally just move the 2 spheres apart from one another, and one sphere has the negative charges, one sphere has the positive charges. And in the final panel, you just move the charged rod away, and now you are left with two spheres, one with negative charge and one with positive charge. And because the spheres are pretty close to one another, they will attract one another. So the negative charges on sphere A are attracting the positive charges on sphere B. But if you move these far enough apart, they would each evenly distribute around the outer surface. So sphere A would have its negative charges evenly distributed around its surface, and sphere B would have its positive charges evenly distributed around its outside surface. And that is charging by induction. And finally, the last topic of this video and the last topic of this lesson is Coulomb's law. And Coulomb's law was discovered by a brilliant scientist and engineer from France in the late 1700s by the name of Charles Augustin de Coulomb, or you can think of him as Charles Augustin de Coulomb, but we're just going to say Coulomb. And he worked out this relationship between the force between electric charges, which we refer to as electrostatic force, to the sizes of the charges involved and the distance between them. Remembering that if you have opposite charges, that is a positive and a negative charge, they're going to attract. And if you have like charges, two positives or two negatives, they will repel, as shown in this diagram. And what Coulomb discovered from his measurements was that electrostatic force is proportional to the size of the first charge, and it's also proportional to the size of the second charge. That's not too surprising. And because it's proportional to both charges, it's also proportional to the product of the two charges. In other words, it's proportional to Q1, charge 1, it's proportional to Q2, charge 2, and it's also proportional to Q1 times Q2. So if you increase either charge or both charges, the force will increase by the same amount. You double one charge, you double the force. You double the other charge, you double the force. You double both charges, you double the force, and then you double the force, which is 4 times the force. If you double one charge and you triple the second charge, that means you double the force, and then you triple the force, which means you have increased the force 6-fold. Now, the second thing that he was able to determine from his measurements is a relationship between the electrostatic force, F sub E, and the distance between the charges. And what he found was that as you increase the distance, the force decreases. And that's also not surprising. But he found that the relationship was that the force was inversely proportional to the square of the distance. And because the force goes down when the distance goes up, we say that the force is inversely proportional to the square of the distance. So this is another example, like gravity, of the inverse square law, where the force is inversely proportional to the square of the distance. And what that means is when you increase the distance even by a little, the force will decrease by a lot, because the force decreases with the square of the change in the distance. And contrary-wise, if you decrease the distance, the force will go up a lot. So one example of this relationship would be if you increase the distance 3-fold. In other words, you move the charges 3 times further apart. Well, if you increase the distance 3-fold, you will decrease the force 3-squared-fold. In other words, you will decrease the force 9-fold. And the formula that Coulomb worked out based on these proportionalities is shown here. F sub E, that's the electrostatic force between the two charges, is equal to some constant, K, that we now call Coulomb's constant, times the size of the first charge times the size of the second charge. That's why we have absolute values. We don't care whether they're positive or negative. We just use the positive version in the calculations. And all of this is divided by the distance between the charges, r squared. Now, when you're actually doing these calculations on your own calculator, you'll notice there's a large Coulomb constant, and you'll frequently have two very small values for your electrical charges, your Q values. In other words, it'll be very small numbers of coulombs for each Q value. And as a result, several of your input values will be in scientific notation. So it's very important for you to become comfortable using scientific notation on your particular calculator. And this is why I have created a separate video that I'd like you to watch if you're not comfortable. And this will walk you through the definitions of scientific notation, how to convert it on paper, and how to use it on a calculator. All right, so why do we keep the charges as absolute values? Why are we making them all positive in our calculation? Because we just want to determine how big the force is. It could be an attractive force, it can be a repulsive force. If both the charges are the same sign, in other words, they are like charges, positive and positive, or negative and negative, the force will be a repulsive force on each charge. Remember, each charge will have the same force on the other charge. They will both be repulsive in that case. If the two charges have opposite signs, positive and negative, negative and positive, the force that you calculate will be an attractive force on each charge. So the forces will be pointing towards each other and they will be of equal size. Now, before we go on to a practice problem using Coulomb's law, I want you to take a look at this comparison between Coulomb's law and Newton's law of universal gravitation, which incidentally Newton worked out 98 years earlier. And you should notice a number of things. First of all, the structure of the two formulas is extremely similar. In the right formula, the formula for gravitational force, you see it's equal to some constant. That constant is capital G. And we multiply it by two masses because masses are what are responsible for gravitational force. And then we divide it by the distance between those two masses squared. In the case of Coulomb's law, we're again taking a constant, a different constant, Coulomb's constant, and now we're multiplying it by the two charges because charges are what are responsible for electrostatic force, and then you divide that again by the distance squared. So the formulas are very, very similar. In particular, I want you to notice that both forces are inversely proportional to the distance squared. In other words, both forces obey the inverse square law. But one thing you should note is that while electrostatic force can be either attractive or repulsive, so far we believe that gravitational force can only be attractive. So if you have two masses, they attract one another. Now maybe there will be some future physics discovered where there can be a negative gravitational force, but to date, we only know that gravitational force is attractive. All right, so let's take a look at a practice problem using Coulomb's law. So this problem states two charged objects, object A with a charge of negative 6.4 times 10 to the minus 10 coulombs, and object B with a charge of negative 2.7 times 10 to the minus 10 coulombs, are separated by 0.00039 meters. Part A says, what is the electric or electrostatic force between them? Well, we have two negative charges, so we know whatever force we calculate, it's going to be a repulsive force. And we have object A, and we have object B, and that's the charge for A, that's the charge for B, and we have a distance between them of 0.00039 meters. So how do we calculate the electrostatic force between them, the electric force between them? Well, we use Coulomb's law. Coulomb's law says that the force due to electrostatic attraction or repulsion is equal to some constant, Coulomb's constant, times the absolute value of charge 1, that's Q1, times the absolute value of charge 2. And that's divided by the distance between them squared. That's the distance R right there. So now we just plug in the numbers and we get 8.99 times 10 to the 9. Don't forget your units. This is Newton meters squared or Coulomb squared. And that's the value of Coulomb's constant times each of the charges, and we don't include the negative signs. We only want the absolute values of our charges. 6.4 times 10 to the minus 10 coulombs times 2.7 times 10 to the minus 10 coulombs. Yes, this is a very small amount of coulombs, but remember, a coulomb is an enormous amount of charge, so this is actually still a significant amount of elementary charges. And then we divide that by the distance between the two charges squared, which is in meters, and then when we square it, of course, that'll be in square meters. And I'm just going to show you how the units work here. This will become meters squared, which will cancel these meters squared. This coulomb and this coulomb will cancel the coulomb squared, and you'll notice the only unit left will be in newtons, which is what we want for a measurement of a force. Forces are always in newtons. So now we plug this into our calculator, and you can always do the square first. If you do that first, you'll get a value of 1.521 times 10 to the minus 7, and that's meters squared. Plug this into your calculator. If you're not sure how to use scientific notation on the calculator, please review the video on scientific notation. And when you plug that in, you will calculate an electrostatic force or an electric force of 0.0102 newtons. And that is our force, and we know it is a repulsive force in this case. So question B says, in which direction are the electric field lines around charge A and around charge B? It's not asking you the direction of the force. It's asking you the direction of the field lines. And one thing we know about field lines is anytime you have a negative charge, if it's a negative charge of any kind, the field lines always point inward. So you would get something that looks like this. And if these charges were completely separated from each other, you would get A, which is a larger value than B. You would get a lot of field lines, and B, you would get fewer field lines, but all the field lines would be pointing inward. But because these charges are near one another, you still get the field lines coming into the negatively charged A, and you can draw those field lines. But you have charge B over here, which may not be quite as strong as A, so there'll be less field lines. But again, you'll have field lines coming in to B because it's a negative charged object. They're both negatively charged field lines, always come in. It does not matter what the other charge is. But if you have two negative objects near each other, both the field lines have to come in, but they can't be touching one another. So they essentially just avoid hitting one another, and you end up with something like this, where the field lines keep away from each other, but they all point in towards A and they all point in towards B. And to show that A has the larger negative charge, you can just have more field lines pointing into A if you want to make it more accurate, at least semi-quantitatively. And that would be it. So part C says, in which direction is the electric force pointing? Hint, review the law of charges. Well, the law of charges is what I mentioned at the very beginning of this problem, and that is that if you have two positive charges, they're going to repel. If you have two negative charges, they're going to repel. And if you have a positive and negative, or a negative and positive, they will attract. And these arrows represent the direction of the electric force in each of these cases. And if you want to be complete, I'll just put a negative and positive, which is also attractive. So we have two combinations that are repulsive, and we have two combinations that are attractive. And in this particular case, we have A, which is a negative charge, and B, which is a negative charge. And A is a larger negative charge, but it doesn't matter. They're both negative, so they will repel each other. And the force on each other will be exactly the same, and we know that from Newton's third law. Newton's third law says the force of B acting on A, which is this force here, it's acting on A, is exactly equal to the force of A acting on B, which is that force right there. So the force directions will be represented by these arrows that I'll put in bold here, and they are pointing away from each other because they are repulsive forces.
So note what this means is that no matter how big or small each of the charges are, no matter what sign each of the charges are, the forces will always be pointing in opposite directions. That is, whether they're repulsive or attractive, the forces will always be equal and opposite in direction.
And that concludes this video and lesson 11B.